Hello, everyone. This is Yonggan Fu from Rice University. Today, I will present our work, CPT, Efficient Deep Neural Network Training with Cyclic Precision. Here's an overview of my presentation today, and I will start from the background and motivations, and then go through the proposed CPT framework and the evaluational results. Recent breakthroughs achieved by deep neural networks has been powered by big data and big computers. However, this also brings significant challenges for DNN training, including the prohibitive training cost for training a complex model on large-scale datasets, as well as huge carbon emissions. Therefore, efficient DNN training is important to address the challenges. Low precision training is one of the most promising efficient training techniques, which reduces the computational cost from the most fine-grained bit level. Here's an overview of the existing low-precision training methods. They quantize the weight, activations, gradients, and errors during the training process to save the computational cost. However, existing low-precision training methods assume the same precision along the whole training trajectory, which leaves a large room for further compression. And they also suffer from large accuracy drop on the low training positions. So the two limitations here motivate us to raise the question that whether a high training precision along the whole training trajectory is always necessary towards a decent accuracy. To answer this question, we propose the CPT framework and we list our contributions here. First, we have the following interesting findings that DNN precision has a similar effect as the learning rate in DNN training. And dynamic precision schedules help DNN generalization. Based on the two interesting findings, we propose the CPT framework with a cyclic precision schedule during training to push forward the accuracy and the training efficiency trade-offs. We evaluate our CPT framework via extensive experiments on 5 datasets and 11 models across computer vision and natural language processing tasks to validate the effectiveness of CPT in boosting both training efficiency and accuracy. Next, I will introduce the motivation hypothesis of CPT framework. First, we assume that DNN precision has a similar effect as the learning rate. So this is inspired by the previous work that noise can help DNN training, and the large initial learning rate helps DNN learn more generalizable patterns. So these observations motivate us to rethink the role of quantization in DNN training. So to validate our hypothesis here, we do the following set of experiments. We train the ResNet 38 and 74 on the CIFAR 100 dataset for 150 epochs, and we adopt full precision and the standard piecewise learning rate decay settings for the last 80 epochs. And we vary the precision and the learning rate in different experiments for the first 80 epochs. So as we can observe from the table here, when we gradually reduce the initial learning rates in the first 80 epochs, training with lower initial precisions consistently lead to a better accuracy. For example, we're adopting the lowest initial learning rate here. We can observe that training with 4-bit will lead to a 1.5% higher accuracy compared with training with full precision. So this indicates that low precision with large quantization noise helps DNN training exploration like a high learning rate. Second, we assume that dynamic precisions help DNN generalization. So this is also inspired by previous work that DNNs learn different patterns at different training stages, and dynamic learning rate schedules help improve optimization in DNN training. So these observations combining with our first hypothesis motivate us to design a dynamic precision schedule in DNN training. To validate our hypothesis here, we compare the performance of static precision training with progressive precision training, which progressively increase the forward precision from 3-bit to 8-bit. So as we can observe from the learning curve here, progressive precision achieves a slightly higher accuracy with notably reduced training cost because it adopts lower precisions in the training process. And we can also observe that progressive precision training led to a better local minima with wider contours when we were visualizing the contours of loss landscape during the training process. So based on the two motivating hypotheses here, the next question we want to raise is that what kind of dynamic precision schedules would be effective while simple to implement for different tasks and models? So we propose the safety framework, which cyclically schedules the precision during training to balance the cross-grained exploration via low precision and fine-grained optimization via high precision, as shown in this figure here. Although there are different kinds of potential implementations for our safety framework, we adopt a cosine manner CPT, as shown in this figure here. And we also propose a precision range test to automatically decide the lower precision bound based on the difference between the training accuracy of consecutive iterations for the users with little low precision training knowledge. And we also compare the static, progressive, and cyclic precision training here. And we can observe that CPT achieved a 0.91% higher accuracy with a 36.7% reduction in training computation compared with the static precision training, as observed from this learning curve. Next, I will show the evaluational results of our CPT framework. So we evaluate our CPT framework on 11 models and 5 data sets across computer vision and natural language processing tasks. And we also compare CPT with 3 SOTA low precision training baselines. So here's the results of CPT on the CFA100 dataset. And the x-axis here is the training computational cost in terms of the bit operations. And the y-axis here is the test accuracy. And we evaluate CPT across different models and different precision settings. And the red point here are the results of CPT. So we can observe that CPT consistently outperforms all the baselines in accuracy and efficiency trade-offs. And we also benchmark CPT against cyclic learning rate on top of static precision training, which is the green point in the figure here. However, we can observe that cyclic learning rate leads to a negative effect in accuracy on top of static precision training, indicating that CPT is more applicable in low precision training scenarios. And we also evaluate the scalability of CPT on the ImageNet dataset, and we can observe that CPT also achieves a reduced computational cost with a comparable accuracy. And here we want to highlight another perspective of CPT as a technique to boost the training optimality. So we can see that CPT with a relatively large precision range leads to a 0.91% and a 0.84% higher accuracy over the full precision counterpart on ResNet 18 and 34, respectively, on ImageNet datasets. So for more results and experiments on the natural language processing tasks and more evaluation studies, please refer to our original paper. And that's all for the presentation.